visiting us from NYU. David is with the computer science department and also with the data science program, which is actually a 2-year graduate program in data sciences. And I hear that you're going to start a PhD program pretty soon?
Starting this year. Applications will be due in a month and a half, so please do apply if you're undergrad.
Okay,
No undergrad, sir? Okay.
The other thing I found out...
Tell your undergrad friends.
The other thing I found out yesterday that he's in this little corner of NYU with Rob Fargus, who was our Windale speaker, and Jan de Koon. So now that we have David here, we just need to get Jan over so we can complete the triangle. So David gave a terrific talk on what machine learning can do for healthcare yesterday. It's really nice to see a whole range of methods and algorithms from very simple and practical to very fancy, sophisticated. And the amazing thing is that in this entire range, many of these are now deployed in hospitals, being accepted by clinicians and making a real difference. And that's, a lot to say if you've ever dealt with this community. It's very conservative. They want to be very sure about how they change systems before they accept anything. So one thing David forgot to mention in this very long talk with all the excitement is that he is looking for students. So I'll give you a plug-in for you.
Yes, thanks.
Since you skipped that slide. All the way from undergrads to postdocs and professional software engineers. If that's something that interests you, don't leave right now, but eventually you might want to catch up with David, right?
Thank you.
So without further ado,
So, thank you, Joydeep and Sujay for the invitation to come here. So, today I'll be talking about structured prediction. Structured prediction is something which I've been working on for about 8 years now. And the goal of today's talk is to start to put a theoretical framework and provide some answers to questions that have been perplexing me and much of the field for the last decade, where we've seen that approximate inference algorithms used for these structured prediction problems work much, much better than they should work in theory. So today I'll be aiming to first give you a new way of thinking about structured prediction, and hopefully within this new framework I'll motivate that there is some theoretical analysis that we can do, and there are many, many open questions that I hope many of you start exploring in the future. So let me first take a step back and tell you what do I mean by structured prediction. So structured prediction is an area of machine learning which, rather than trying to do, let's say, binary or multi-class classification, it looks at supervised prediction problems that take a data element as input and try to predict a structured set of outputs. So for example, you might take as input an image, and your goal is to predict for every single pixel in that image, is it foreground or background, shown here on the right-hand side. Right? So that can give you a segmentation of the image. Or for example, you might be given as inputs 2 images. One you could think of as the image coming from your left eye, and one being an image that comes from your right eye. And by looking at the disparity in how much shift there has been from the corresponding pixel in your left eye to the corresponding pixel in the right eye, you could figure out the depth of objects from the viewer. Now this is something that humans do really well, but which is very difficult to automate by a computer. But nonetheless, one could try to tackle it as a structured prediction problem, where the input is these 2 images, and the output is, for every single pixel in the left image, the amount of shift to get to the corresponding pixel in the right image. And that gives you then the depth map. Another very different type of example comes from natural language processing, where you might be given as input a sentence, like John saw a movie yesterday that he liked, and the goal is to understand the syntax of the sentence. So in particular, one could look at the dependency parse, which tells you how do words relate to one another. So you'll recognize that John modifies the verb saw. So this is the noun, this is the verb. You'll recognize that a movie that he liked, he saw a movie yesterday that he liked, and that he liked talks about the movie, right? So in trying to learn this dependency parse, you understand something about the structure of the sentence, which could then be used in many downstream applications like machine translation, for example. But our goal is to really take that sentence and predict that whole parse tree. Right? And so if you start to think about how you would formalize that as a machine learning problem, it raises a number of new questions about how do you quantify the goodness of and possible output, and how do you search through that output space. And that's something which structured prediction deals with very well. The way that one formalizes this is that one defines a score on the input x, x is the set of inputs, like for example images, and on every potential output y, both x and y are vectors, which is going to be high if y is a good labeling for the input x, and low if y is a bad labeling for the input x. Right, so y would be something like an assignment to every single random variable corresponding to each pixel of whether it's foreground versus background. Now, as you can imagine, these scores could be very complex functions. In order to try to get traction on both how to fit them from data and how to do inference using them, one typically considers more structured versions of these scores. For example, you could imagine in an application like foreground-background segmentation that one could formalize this score in terms of local relationships between pairs of adjacent pixels. And so you would get a model that looks like this grid-structured model, where that score then decomposes into a sum of scores over edges of this graph, which correspond to nearby pixels, of these local scoring functions, which look at the whole image and give you a value for how likely each pair of pixels corresponding to that edge are foreground, background in any combination. So this is a local score, and the global score is obtained by a sum of these local scores. And typically also there are these single node terms that just look at each pixel in itself. And this would tell you, for example, the affinity of any one pixel to be foreground versus background. In this picture, you see that the horse is black and the background is not black. So if we knew that our horses were always black, this would be looking at the color of the ith pixel, and it would look at the color of that pixel, and if it were black, it would say it's more likely that this yi is going to be a foreground versus background. Any questions so far? I don't have that many slides, so this is an opportunity to be interactive throughout the talk. If you have questions, we could also leave more discussion time at the end. Yep?
You want to have a loss function that also measures that everything is in the foreground is a continuous.
Oh, great question. So the suggestion was perhaps this could be a bad scoring function, or there's more prior knowledge that you could put into it. For example, one might recognize that objects are typically contiguous. So you might even argue that there's a convex, or maybe not convex, but a closed set, which would be the foreground object. And you might like to put another score function in here, which encourages that you have such closed regions in the foreground. That's absolutely right. And as people go to more and more advanced structured prediction models, you start to include higher order terms that include that type, that would enable you to use that type of prior knowledge within your prediction algorithm. For today's talk, however, I'm going to focus on this somewhat simplistic pairwise model setting. And actually, I'm going to even narrow down a little bit further to talk about just binary labels, where yi is either +1 or -1, such as in this foreground-background segmentation problem. Now, the reason why I'm doing these restrictions is because I want to start to build some theory here. And these questions are extremely challenging from a theoretical perspective, even in that simplest setting. So you're right, in real-world applications, one would want to do that, but we're going to right now focus on the sort of somewhat simplistic models. So given that scoring function, one can define a posterior distribution over the set of possible labelings y conditioned on the input x. And the typical way to do that is using what's called a Markov random field or undirected graphical model, where you simply exponentiate that score, and that then gives you a non-negative number for every possible assignment to y. And in order to get a distribution over labelings y, one needs to normalize this in order to make sure that it sums to 1. And so this z of x is the partition function, which enforces that you have an actual distribution over labelings. Now, given such distributions, in order to actually solve the prediction task, there are a number of probabilistic inference queries that you could do using that distribution. For example, conditional random fields will try to fit this model, and then it'll try to predict for every label, whether it's, for example, foreground versus background, by doing marginal inference in that model. By taking this joint distribution, which is a function of all possible labelings, and looking at any one pixel to compute the marginal probability that that pixel is foreground versus background, which in itself, by the way, is a very hard inference task. Once that inference is done, one can look at the argmax of this to see, well, is yi equals 1 more likely than yi equals -1? If so, we predict foreground, otherwise we predict background for that pixel in itself. Now, there are other ways to try to do prediction using these models. For example, rather than looking at each individual variable by itself, one could look globally for the most likely assignment. And that would be corresponding to map inference, where you try to find the y which maximizes the full posterior probability of labelings given the input x. So these are two different ways of trying to do prediction. And actually, one of the things that I'm going to be trying to get traction on is what are the trade-offs between different prediction methods using your underlying distribution when you're trying to solve specific tasks. So the starting point for this work is the observation, which is always the starting point in any paper on approximate inference in machine learning, which is that most real-world models that are used in real-world applications have that both the marginal and map inference tasks are NP hard, or computationally intractable. Now, nonetheless, what we've found over the years is that a whole wide range of heuristic inference algorithms nonetheless do really well for structured prediction. So let me give you a couple of examples. Hold your question until the end of these examples. So look at stereopsis. These are the inputs. This is the desired ground truth depth map. And if you take a very simple pairwise model like the one I showed you on the previous slides, and you used an approximate inference algorithm based on graph cuts to try to find the most likely assignment given that conditional random field, what one gets is the following prediction. Now compare this thing on the far right hand side to the one in the middle, and you'll recognize they look quite similar. In fact, the prediction, this model is doing a pretty good job at figuring out the depth of each pixel in that image. Now here's another example coming from image segmentation. This is the ground truth. And this is the prediction given by, again, a map inference algorithm. Now, rather than based on graph cuts, it's based on solving a linear programming relaxation or using dual decomposition. These are equivalent quantities. Do you have a question?
Yeah, so regarding this hardness and the previous slide, which had the, if I just have a grid icing model,
Yes.
Which is the binary case of what you have,
Yes.
Then is that known to be hard?
It is. So for all of these problems, you have both these pairwise potentials, and you also have these single node potentials, like what I told you earlier, talking about the affinity of every pixel to be foreground versus background. Even the map inference problem in those models is NP hard.
For grids?
For grids, for any planar graph, as long as you have those external fields. I'm going to return to this point in just a few slides.
Three widths of a grid is huge, right?
But bad tree-width graphs are much bigger than the set of grids.
Yeah, we'll return to this, so don't worry. So the goal of this talk is to try to answer this question of why these approximate inference algorithms are actually working much better than we would expect. And part of what I want you to start to recognize already on this slide, I'm doing something a little bit subtle here. I'm priming you to think about inference algorithms in a particular way. In particular, I'm telling you, look, this looks similar to that, and this looks similar to that. Right, so I'm priming you to start to think about how to quantify how good or bad an inference algorithm is based on the Hamming distance, or some error metric of the prediction given by your model and inference algorithm and the ground truth. But that is exactly not what most of the approximate inference community does when they talk about the hardness of inference. When they talk about the hardness of inference, they usually talk about that combinatorial optimization problem I showed here, and they talk about the ability of an approximate combinatorial optimization algorithm to find a high objective value solution. And then they'll say, oh, it's not even possible to give a p-task for this problem because finding an assignment y which has close to optimal probability is NP hard. Right, but that is not what we care about here. What we care about for structured prediction is this notion of error metric between the predictions, not objective value. And those two can be very different from each other, and the theoretical results that we give will be focused on this problem, which is the one that the community should be caring about. And so just to start to return to these points of, well, are these problems actually intractable? What is known about them? Well, there's been a lot of work in the probabilistic inference community to try to characterize what are classes of tractable models. For example, if you have a tree structured model, meaning that graph of local scores is only defined over the edges of a tree, then one could show, or even a low tree width graph, then one can do all of these inference problems in polynomial time. But the real-world applications aren't low tree width graphs, they're high tree width graphs. And neither do they have any known structural property, for example, submodular potential functions or anything similar to that. But intuitively, these problems are close to something tractable. And in this analysis that I give, I'm going to quantify for a very specific application what I mean by close to something tractable. And as I've been insinuating, we are going to demonstrate a setting where one can provably, in polynomial time, obtain small Hamming error, where Hamming error is measuring the sum over all of the labels of the indicator of whether your prediction y hat for that label is equal or not equal to the ground truth, yi. So the key questions for the theoretical analysis are as follows. First, I think it's essential that we start to ask what are the information theoretic limits of structured prediction. That's to say, one needs to try to understand, given the task at hand, how good can you hope that any inference algorithm can do, even ignoring computation time, at predicting what that underlying ground truth labeling is. So for example, if you looked at the two problems I showed you earlier, the image segmentation, the stereopsis problems, those are examples where information theoretically, we know the information is there. You know, if a human were asked to do this image segmentation problem, and you were to measure, for example, inter-rater reliability on segmentations given the same image, you're going to get very high reliability, and humans are able to do the job very well. So information theoretically, the content is there for those problems. Second, we want to understand what are the computational and statistical trade-offs here. So for example, one interesting question is, how much worse would map inference be compared to marginal inference? Now the reason why this question is relevant is because if you care about Hamming error, what I showed in the previous slide, then one can prove that marginal inference is information theoretically optimal. And map inference is only going to be worse than that. But how much worse is it? For example, marginal inference involves a much harder problem. It's a counting problem. So if you're familiar with computational complexity, it's going to be something like, counting the number of satisfying assignments hard. Whereas map inference is only NP hard. And so the difference between map inference and marginal inference from a computational complexity perspective is very high, but it may not be so different in terms of the ability of doing good prediction in terms of Hamming error, and that's one of the trade-offs that we're going to see. Second, one would like to ask, well then, suppose we restrict ourselves to polynomial time algorithms, what is the best prediction accuracy that you could get in polynomial time? And third, because many of the heuristic inference algorithms that I've worked with and other people have worked with are based in solving linear programming relaxations that we found to be much better than we think they should be performing based on the theory, I'm also interested in understanding provable guarantees specifically for polynomial time algorithms based on linear programming relaxations of map inference. I'm not going to answer all of these questions. I'm going to give you a model where I answer the first question, the second question, and the third question, and the fourth one I'm only going to give you empirical results for. And as I'll discuss towards the end of my talk, it's an open question how to generalize our proof technique to actually analyze the LP relaxation. So in order to try to answer these questions theoretically, we need to have some way of relating the ground truth labeling with the predictions made by the model and by the observations that you get x. So we need to relate ground truth y with your observations x and your predictions y hat. So in order to do so, in this work, we analyze the following generative process. We assume that we have a set of binary labels that we want to predict, y1 through yn. They're +1 or -1. Think of +1 as foreground, -1 as background in an image segmentation problem. And our analysis assumes that we have observations about y, noisy observations, which are of the following nature. For every random variable, every pixel of your model, you get a local observation xi, which is equal to yi with probability 1 minus q, and equal to the flip of yi with probability q. So q is your node noise rate. We also assume that we have edge observations, xij, for every edge of your graph, which measure whether the two endpoints I and j have the same sign, whether they're both +1 or one's +1, the other one -1. So that's to say it's equal to yi times yj, right? Yi and yj are +1 or -1. Yi times yj with probability 1 minus p, and the flip of that, the noisy view of the edge agreement with probability p. So p is the edge noise of the observation. So let me give you a picture of what you should expect to see in this setting. So suppose that the ground truth assignment was all -1s, which I'm denoting here as just white nodes. If going through this generative process, the observations you get x are generated from y via this noisy process. And so, for example, red here denotes +1 observations. You'll notice that there are a lot of red nodes here. Those are noisy observations of the local nodes. And black edges denote same, red edges denote different. So you'll see that there are a few of the edge observations that are different, but because the ground truth is all -1, we want they should all be black. So the red edges here are the noisy edges. So this is the input to your prediction algorithm. And what we'd like to do is come up with an algorithm that can take this input and predict what it thinks y was. So it outputs this y hat as a function of x, which you see here gets Hamming error 2. Yes?
So if you didn't have the edge things, it would be the standard, it would be a standardizing model.
Right, so if you didn't have the edge observations, then the best you could possibly do is just predict according to xi. You could think of that as a typical machine learning prediction problem. It's these edge observations that make it into a structured prediction problem.
So what is an example where you have edge variables of this type?
I'll give you an example on the next slide.
So the edge signal that you get is independent of the node. So when I see black between red and white, that's not a noise.
Correct.
Correct.
Correct. It's assumed, the generative process assumes that they're independent. Each one is drawn independently. Now, the interesting setting for machine learning is one where the node noise Q is close to 1/2. Right, what that means is that if you were to just look at the node observations, you're going to do pretty bad at prediction. One really needs to look at the edge observations, these xij's, in order to get any non-trivial prediction error. In particular, there's no correlation decay in this model, right? So you can't just look locally around any one random variable in order to predict what its value is. You have to integrate evidence from all over the model in order to do good prediction for any one variable. And this is a very important point. So the theoretical analysis is quite easy if you assume Q to be low. But the interesting scenario from a practical perspective is when Q is large, somewhere close to the information theoretic limits.
So whether you have correlation decay or not depends also on P. It's not just a function of Q.
Yes, I'm assuming P is a constant here.
But for example, if P is half, it's useful.
Sure.
Right? So
Yeah.
you assume, and if P is very close to 0 or 1, it's super useful.
Yes. So our analysis so the first step of, I already primed you with the questions you should ask. The first question is, what are the information theoretic limits as a function of P and Q?
No, but I guess what I'm saying is that you could have correlation decay even for Q being close to half or equal to half, depending on the value of P. Right? So this. Yeah,
so I assume that, sure. We can talk about that later. Yeah.
Well, then you wouldn't know black and white. You couldn't.
Yeah. So but up to global consistency, you could know.
So under that model, then the maximum likelihood estimator can be shown to be as follows. So that is to say, given the observations x, consider an inference algorithm which simply tries, if the inference algorithm knew what the underlying generative model was, then the best possible prediction, well, this is actually not true. One possible prediction algorithm would be to try to find the maximum likelihood estimate of y given your observations x. And the form of that would be as follows. It's a sum over the edges of the edge observation xuv times yu yv, where yu yv are the things you're optimizing over, times this constant. So this edge term, what it asks is, if xuv is +1, then you really want yu and yv to have the same sign so that this term is positive. And remember, we're trying to maximize, so we want this to be as large as possible. If xuv is -1, then we want the two of these to have different signs, in which case, again, this is positive. In addition, there's a second term, which is a summing over the nodes of the node observation xu times the label yu. And again, if xuv is positive, this is asking that yu also be positive, and vice versa if xu were negative. Now these two terms are weighted by this constant log 1 minus p over p and log 1 minus q over q, which tell you how much you should weight the different evidences. So for example, if q were 1/2, then this ratio is 1, the log of 1 is 0, and this term just disappears. Right? So as q gets larger, this term gets less and less important compared to the edge term in the overall objective function. Now this is the maximum likelihood estimator. What one could show is that for the Hamming error, knowing that this is the right generative model, the best possible prediction would be given by marginal inference with an energy function that's built like this. So you exponentiate that, you renormalize, and you get that distribution. If you did marginal inference with that distribution, that would be the best possible prediction you could do in theory. So what I'd like to do now is to try to relate this back to the real world application that was motivating this with image segmentation. To try to connect where these x's are coming from when you think about an actual image. So if you think about a conditional random field which tries to, given as input an input image, now I'm calling it z because x is reserved for something else I showed in the previous slide. So given an input image z, one could imagine learning a model which tries to give a posterior distribution over labelings y hat given z, and it might be this pairwise model that I show up here. The weights of this model, beta uv, would be given to you by some function of the input z and your model parameters theta, and similarly your single node weights, beta u, are also given to you by some feature function dot producted perhaps with a weight vector theta. Those are typically learned from data, and then prediction will attempt to given these functions f and given a new input z, will attempt to do something with this distribution. Now I want you to compare this to the form of the maximum likelihood estimator I showed in the previous slide. Let you stare at that for a second. So the y's are in common, right? So if you look at this term up here and try to match it to this term over here, you again have yu times yv, yu times yv, except now there's this beta u v, which takes the place of this x uv in log 1 minus p over p. Similarly, if you match up these terms, you see there's a beta u here, which takes the place of this x uv times log 1 minus q over q. So intuitively, what is going on when you have a conditional random field is that your edge and node potentials, after learning using real data, are intuitively playing the role of giving you noisy evidence about the underlying edge and node true values. Right, so beta uv plays the role of x uv, and beta u plays the role of xu. And the strength of those edge and node potentials is going to be a function of how important that edge or node signal is. That's what these constant terms are on the side. So, for example, if it turned out that looking at whether the two endpoints have the same or different values gives you no information about predicting the underlying assignment, then after learning, you'll learn that the beta UVs that you'll get in your model are going to be all 0, right? Because it's just not useful for prediction. If your learning algorithm decides to keep those potentials around, it's because they're actually useful. And because you've done learning, you've in essence calibrated your potential functions so that each resulting feature is providing new evidence about the underlying ground truth. So this is the way I want you to be thinking about doing structured prediction, and this is the way I want you to be thinking about how to analyze structured prediction problems in terms of the potential functions providing noisy evidence about some underlying ground truth. And from here on, what I'm going to do is I'm going to analyze this model I've shown here, where I'm making a very strong assumption in particular. I'm assuming, for example, that every edge is equally important, or the noise rate in every edge is the same. Right? So that is to say, instead of p being p sub ij, it's just a p. And similarly, I'm going to assume that the node observations are equally important, just one node noise rate. Of course, in the real world, these are going to differ per edge and per node. And in fact, one can show that our theoretical analysis will generalize to a non-homogeneous setting as well, but I'm sticking with this simple setting to try to give you the big picture.
So it's not image-dependent weights. It's
So they're not image-dependent weights, correct, in the analysis that I'll show.
So there's no learning phase at all?
No, so I am just talking about the hardness of the inference problem, assuming that you've done learning already, and that the goal of learning was to get these node and edge potentials, which are as good as possible, but noisy views of the underlying ground truth. And then assuming that you have them and that those noisy views are bad with these error rates P and Q, we want to ask to see how good you can do a prediction as a function of those noise rates. Yep.
So the first part of your objective is just like a min-cut kind of objective.
Yep.
It's just but then you have the second part.
Yep.
And so the overall objective is it hard to solve in general?
Yes.
Okay.
Even this maximum likelihood estimator is NP-hard in general, and I'll just skip ahead for a moment. Even when the graph is planar, this maximization problem is NP-hard. So this problem, so I've motivated from structure prediction. I've come at it. I've been interested in it because of structure prediction. But I talked to Alex. I don't know if you remember going back to 6-7 years ago in your car driving, right? I was asking you about LDBC codes and trying to really understand recovery results for them, because for the last 7 years I've been trying to show these results for structure prediction. And I recognize that in order to try to theoretically analyze this, I need to build on these tools coming from many different communities. So for example, you could view the same problem from a coding perspective, right? If you viewed XUV as a noisy version of the parity of YI and YJ, then this exact same problem I just talked about can be related to coding theory. Although this is a very bad code. So what one can show, and I'll show soon, is that this can't be used for errorless transmission, meaning as long as your graph is somewhat sparse, you will not be able to perfectly recover Y. As long as P is non-zero. It also relates to correlation clustering, right? You can view these, you can view this as a two correlation clustering problem where there are two clusters corresponding to YI being +1 versus -1, and where you have edge observations. Except unlike in the typical analysis of correlation clustering, where people look at, for example, minimizing the number of edge disagreements, here we care about the Hamming error of the clusters that are predicted. It relates to many, many other problems studied in theoretical computer science, such as the planted Klee, graph partitioning, detecting hidden communities. The analysis techniques I've built upon, it won't be obvious, but I spent a lot of time understanding what's going on in the phylogenetic tree reconstruction literature and in percolation theory, which is very relevant to the tools needed to do these types of analyses. And it also relates very closely to another field called synchronization, or angular synchronization, which has been studied, among other people, by Alfonso Bandera, who we just hired at NYU, and looks at precisely the same optimization problem I showed in the previous slide, except they usually look at very different graphs. So they'll look at complete graphs, or perhaps random graphs, or expanders, and in those settings, actually the recovery problem is pretty easy. And it's also not very interesting from a machine learning perspective. In machine learning, we often have these graphs that are, for example, these grid-structured graphs, where exact recovery, or exact recovery with high probability, is simply not an attainable goal. And any theoretical analysis has to be able to talk about approximate or partial recovery, which has been stated in all of these works as a big open problem, how to give theoretical tools to analyze them. So as I mentioned, when this graph is a planar graph,
Can I ask one question? So you're happy if you find a solution that in Hamming distance is a constant fraction away from the optimum? So that's
if that's as well as you could do information theoretically, I'm happy.
Oh, but I'm saying, is that the regime where you because belief propagation and the LP that's where they fail, right?
Yeah, no, so but you're asking the right questions, right? So I want to give an approximation guarantee as a function of the best possible Hamming error.
Yeah. And it will be linear, or it can be sublinear. Would it
anything is of interest.
Okay.
Yes. So on the other hand, however, I told you I would hint at, for this problem, that the inference task is actually close to something which is tractable. And in particular, if one were to ignore these node terms and just look at the graph itself, just look at the edge observations. Then for a planar graph, of which a grid is an example, in fact, this maximum likelihood estimator can be solved in polynomial time. And there are several approaches for doing so. Fisher gave an algorithm based on matchings to do so in a dual graph. Barahona showed that a particularly simple linear programming relaxation called the cycle relaxation, or the second level of the Shirley-Adams hierarchy, these are equivalent, is also exact. So that linear programming relaxation is not tight, it has integer optimal solutions for this optimization problem when your graph is planar. So those are the settings actually that I'm going to analyze in this talk, motivated by what we see in actual machine learning applications. And we see that in fact this term is close, and we're going to build upon that assumption actually. We're going to build upon that fact in giving our algorithm. We're going to show, in fact, a two-step algorithm which first works with this and then works with that, and which we prove will actually get close to optimal performance on Hamming error. So it's going to very strongly build upon this in order to give its polynomial time properties. So before I jump into theory, I want to give you some empirical evidence that this is of interest. And this is the first thing I did when I started working on this problem. Because I formalized the structure prediction task by this generative model, and I wanted to make sure that it had the same properties that I observed in the real world data. So in the real world data, what I found was that solving very simple linear programming relaxations in some cases does do well. And as I improved the linear programming relaxations, I got better and better prediction accuracy. And I've found that across a wide range of applications, including all three of the ones I showed when I motivated this, including the natural language processing one. So what I'm showing you here is an empirical study to see if we see the same phenomena. So on the x-axis, what I'm showing you is the edge noise. As the prediction task gets harder and harder, the edge noise is increasing from 0 up to 0.1. The node noise, Q, I'm leaving fixed to be 0.4, which for a small graph, so the way I chose 0.4 is I looked at, for this graph, 20 by 20 grid graph, how good the recovery can get as you push that node noise higher and higher. And 0.4 empirically is found to be near the information theoretic limit so there's like a phase transition when you go beyond that. So I'm interested in that setting, which is as hard as it can be in essence for a graph of this size. As your graph gets larger, this node noise should be going up as well for it to be theoretically interesting. And on the y-axis here, what I'm showing is the Hamming error, and we want that to be low, right, which would mean you get good prediction accuracy. So in this synthetic setup, I'm assuming that the ground truth assignment is all -1s. I'm assuming that the node noise is 0.4, the edge noise is as given as here, and I'm generating those x's via this generative process that I proposed. And then I'm asking, how do different algorithms do at recovering that underlying ground truth, which I know is all -1s, and I want to see how bad is the Hamming error predicted by each different algorithm as a function of the edge noise. So first I show this blue line here on the very bottom. This is marginal inference, using the model implied by that generative process. One can show that this is information theoretically optimal. As I was saying earlier, in terms of doing exact optimization, it's NP hard, or actually sharp P hard. But for a 20 by 20 grid graph, one can use the junction tree algorithm to exactly brute force perform marginal inference, which is how I'm able to give you this curve. And you see that as the edge noise P is low, as the edge noise P grows, not surprisingly, the Hamming error goes up. Now I want to start looking at polynomial time algorithms. In particular, this curve on the top corresponds to using a pairwise linear programming relaxation. This is in some sense the simplest linear programming relaxation that you could write down for this problem. Notably, it's derived from the map inference or maximum likelihood objective function, not from marginal inference. So this is solving a combinatorial optimization problem, which so there's going to be a sandwich point. Map inference will be somewhere in here. We don't know where it is, and this LP relaxation will only be worse than that in theory. And what we see is that when the edge noise is pretty low, this polynomial time algorithm actually does reasonably well at prediction, but there's a gap. And as the edge noise grows, that gap grows and grows and grows to be quite substantial. And indeed, what one sees is that as the edge noise gets very large, the solution to that linear programming relaxation becomes fully fractional. So it's all 1/2 fractional. Now, there are other LP relaxations, and what particularly struck me and which made me realize that this is probably a good model to analyze is that if you look at this cycle linear programming relaxation, which is just one step higher in the Shirley-Adams hierarchy, you get the following green curve. And notice that for all the way up to edge noise of roughly 0.08, the cycle LP relaxation is getting almost information theoretically optimal performance. Right? Which is the type of thing we see in the real world applications where these relaxations actually do really well at the underlying prediction task. And so this motivates, well, can we give a theory to explain why this is doing so well? Yep?
Do you include cycles of all lengths?
Yes, it includes cycles of all lengths, but one can solve it in polynomial time either by using a separation oracle or by triangulating the model first, in which case only triangle inequalities are sufficient.
So triangulating is the same as junction tree, as making a junction tree operator?
No. These are triangle inequalities of a linear program, in a linear programming relaxation. The tree width of this model is still very high. I mean,
so you don't mean triangulating the graph in this, because triangulating the graph sometimes means the same thing as what the junction is.
You would triangulate the graph, and in essence what you get is a almost complete graph out. Well, really it's not a complete graph, it's a tree width 20, right? It's tree width the width size, or column, or height size.
But that's not what you mean by triangulation.
Triangulation is perhaps not the right word. If one were to, what's called, use a lift and project method to construct all three-way interactions and enforce constraints between all three-way interactions, despite the fact that this basic LP relaxation only needs edge-based interactions, then one can get an equivalent relaxation as a cycle LP relaxation, which is tractable to solve. All of this is in my PhD thesis in detail, but for now you just have to realize that, so believe me, I say this is tractable.
So like all triangles is order n cube number of constraints.
Yep.
All cycles is much higher.
Right, but you only need n cubed to solve this.
I see.
Yes.
I see.
Is there something special about this problem? Because that's not true in general.
Yes, there's a lot that's special about this problem. It is true, like in my thesis I show that it is true in general, if you do it correctly. So for all Markov-Frenum fields, you get this type of property. But this we should take offline. It's starting to get very technical. I don't want to go into the details of that in this talk. Okay, so I'm not going. So the punchline is I'm not actually going to prove that this does optimal. That's an open question. I don't know how to prove this. Instead, what I'm going to prove is something else which gets close to the screen line.
In fact, it cannot, right? Because it's NP complete to be optimal. Or
No.
it's not?
One should be able to prove, this is the big open question in my mind, I've been working on it already for a couple of years, any help would be appreciated. One should be able to prove that with a very simple rounding out, so this is an algorithm, that this algorithm in fact does get close to information theoretically optimal. Blue is information theoretically optimal, right?
Why?
It does, it happens, right? Here's the proof that it works. And it doesn't have to do just with the size of the graph. You know, if you repeated this, you scale the graph, same thing is gonna happen. So I have empirical evidence, very strong empirical evidence that this is close to information theoretically optimal. It's just a question of how to prove it. And by the way, this answers already the first question, which is about trade-offs between complexity and so information theoretically, this is the best possible you can do in this problem. That's a curve. In terms of what you can do with polynomial time, yes, you can get very close to it in polynomial time. So this is the empirical evidence that the answer is yes, you can get almost the same in polynomial time. The question is just how to prove it. Yep. So after point 1, great question. I think things start to diverge there, actually. I don't remember very well. Point 1 is already, so if you look at this, already by point 1 edge noise, your Hamming error is getting close to 10%. Right, so as your edge noise gets even bigger than that, your Hamming error is just going to continue to grow, and it's not clear that the problem is interesting anymore from an applications perspective.
No, then is that 0.8 transition point very dependent on the size of the graph you're looking at?
Yes, it does depend on the size of the graph, but I'm assuming that you scale Q as your graph size grows. So try to sort of, there is going to be, so as your graph size grows, you get more and more evidence, and the problem becomes easier, and so to keep it interesting, your Q should also be growing.
So the marginal inference, you said it's NP hard, but I guess.
I should have said sharp P hard.
So do we know something about its approximability? I guess
Hard as well.
So it's sharp P hard when you have adversarial X.
When it's adversarial, exactly.
Yeah,
So it's
statistical model.
yes, exactly, and that's the whole point, right? So it's hard when you have an adversarially chosen X, but we are in this different world, which is motivated by those by this related work, right? This is a completely different world that we live in, and that I think we need to be living in when we analyze these problems of statistical recovery, right? These X's are not chosen adversarially; they're chosen because you actually want to do good at this prediction problem. That's exactly the point. Okay, so now I'm going to dive in and answer both of these questions. I'll do it relatively quickly. The first question is, what is the information theoretic limit? You saw that curve. I'm going to prove for you that the information theoretic limit is that every algorithm must have expected Hamming error of roughly p squared times n. N is the number of labels, and p squared, p is, remember, the edge noise. So here's the proof sketch. It's very simple. What we're going to do is we're going to choose a particularly bad distribution on the underlying ground truth assignment y. And then I'm going to demonstrate that no algorithm can do well in that distribution, or given any algorithm, given any algorithm, it will do bad on at least one assignment from that distribution, which then proves that every algorithm does badly. So in particular, I'm going to look at the distribution where, in this checkerboard fashion, we know y. So all these shaded nodes I'm fixing to -1. And the only unknown quantities are the white nodes, which we're going to sample uniformly to be +1 or -1. So this is the distribution that I'm sampling the underlying ground truth assignment y, and then x is going to be a random sample for that y. Now let's call a node ambiguous if for the x that you observe, exactly 2 of the edges around that node are observed to be equal, and the other 2 are observed to be not equal. Notice that as I'm defining it, right, it's a function of what that actual white node was. But let's ask how many of those ambiguous observations there are. Well, there are n over 2 white nodes. And in order for exactly 2 of its endpoints to be equal and 2 to be not equal, you need 4 choose 2 times p squared 1 minus p squared is the expected number of these ambiguous nodes that you're going to get, which is roughly n times p squared. So there's roughly n times p squared ambiguous nodes as a function of the x observations that you do get. Now, for those ambiguous nodes, the best you could possibly do is to just predict according to the node observation, right? And the node observation is going to be wrong with probability q. And so if you put those two things together, you say that the expected Hamming error is n times p squared times q, right? And so that's where you get the lower bound of p squared times n. So it's a very simple proof to show that the lower bound, even in the most optimistic scenario where you know half of the labels, you can't get better than p squared times n Hamming error. But notice, by the way, that as p goes down, as p goes towards 0, your expected Hamming error goes towards 0. So it has the property that one would expect. Now we're going to analyze the following 2-step algorithm. The algorithm first in stage 1 only uses the edge observations. And in stage 2, it looks at the node observations, and it looks at those node observations and says whether to flip or keep the same the prediction y hat given by solving the part of the maximum likelihood optimization problem coming just from the edge observations. So already immediately you should see one thing, which is that this is not an approximate inference algorithm based on marginal inference. It's based on something like map inference, or maximum likelihood, right? And it's definitely a heuristic, because we're not solving the actual maximum likelihood objective. We're splitting it into 2 steps. And because of what I mentioned earlier, the first step can be solved in polynomial time, and the second step obviously could also be solved in polynomial time. So the intuition of this 2-step algorithm is as follows, or what we're going to prove about it is as follows. After stage 1, we will show that either y hat or the flip of y hat is going to be close in Hamming error to the underlying ground truth. And then one can just look at the node observations to figure out which of these 2 settings you should predict. That's what's done in stage 2. So the goal will be to prove this first fact, and the second step is actually pretty straightforward to show. So to do so, And before I run to the theory which proves that, let me just give you the following picture. So this is their two-step algorithm. So if you were to run that in this empirical data sets, it gets this red line here, and notice that for sufficiently small edge noise, it is basically optimal. Right? So we want to try to prove that. So the theorem that we will show is as follows. That two-stage algorithm will also get expected Hamming error of p squared times n, which by the way is the same as our lower bound, up to constant, whenever your edge noise p is less than 0.017. Just want to point out that first point, if you look at this plot, 0.017 is roughly here, and you can see that the performance is pretty darn good even up to 0.04, despite my not knowing how to prove that piece over here. The proof sketch is as follows. It'll be 3 steps. The first step, and the most important one, is the structural lemma, which talks about what the structure of mispredicted or mislabeled nodes must look like. The second will be a counting argument to say that there cannot be too many of those types of big sets. And the third will just be a union bound piecing these together. So the structural lemma, and this is the main tool used in the proof, is as follows. We define an edge XUV, an edge observation XUV, to be bad if it is the flip of what you expect to find. So if XUV is equal to minus YU times YV, we call that edge observation a bad edge. The flipping lemma says that let's let S denote a maximally connected subgraph of G, where every node in S is mispredicted by your algorithm y hat. Or sorry, it's mispredicted by y hat given to you by the output of stage 1 of the algorithm. Then at least half of the edges on the boundary of S must be bad, as defined here. So let's do a proof by a simple picture. Look at the following simple graph, where suppose that the ground truth is all -1, and y hat, the output of stage 1 of the algorithm, mispredicts that middle node, and correctly predicts everything around it. So that's why you see the middle node being red and the other ones being white. Well, the maximally connected mispredicted set here is just that single node. Now let's look at the boundaries of this. Suppose for contradiction that all 4 of the edges on the boundary of this mispredicted node were equals. So that is to say they're not bad edges, they're good edges. Well, now let's look at the let's look at the objective function solved in stage 1 of the algorithm, which is as follows. If all 4 of these edges are equals, meaning that this is +1, then if y2, y3, y4, and y5 are all -1, then y1, when you solve this, must have been -1. That is to say, if you were to flip this y hat from +1 to -1, this objective must only go up, which contradicts the assumption that y hat was optimal, and thus proves that it couldn't have been the case that all 4 of the edges were equals. And one can generalize this argument to see that at least half of the edges in the boundary must have been not equals. All right, so this is the structural lemma we know. We know that any mispredicted set must have a big boundary of bad edges. And that's what we'll build upon in the next step. So let's let delta S be the outer boundary of the set of nodes. So here I'm now looking at a slightly bigger set of mispredicted nodes of size 3. And I'm sort of circling it to illustrate the boundary. The boundary is all of the edges that are being crossed by this cycle. Right, so this is the boundary of that set S, these edges. That boundary is of size 8. There are 8 edges on the boundary of those 3 mispredicted nodes. We're going to call that set S bad if at least half of its boundary edges are bad. The first lemma is that for every set S with boundary size k, the probability that that set is bad is at most something which is exponentially decreasing in the length of that, or the size of that boundary. Which intuitively makes sense because the edge noise is p, and so you expect that this edge, so this edge is wrong with probability p, this edge is wrong with probability p, all of those edges are independent of each other, right? And so the probability that a lot of these are bad is going to be exponentially decreasing in p. The second result is that for every set S, notice that the first result talks about the boundary, but we care about Hamming error, and Hamming error talks about the number of nodes in the set. So somehow we need to connect the boundary size to the number of nodes in that mispredicted set. And to do so, you can use a very simple isoperimetric inequality to show that the number of nodes must be bounded above for a grid graph by something which is quadratic in the boundary size. And as you try to generalize these results to other types of planar graphs, in some sense the expansion of the dual graph is what shows up in this result.
I have a question.
Yep.
Are your results for any planar graph or only for grids?
So the result I'm proving for you right here is for grids, and in our paper we show it for any planar graph of bounded dual expansion, and we also give results for expander graphs with bounded degree.
So is it good for you if you had so expander would be linear, right? So you wouldn't have the square.
Right.
Basically, is that a good thing for you or is it a bad thing for you? That's what I'm missing.
It's a good thing. That only improves the result. The Hamming error would, so basically the bad case is when this so you want this boundary size to be large relative to the mispredicted nodes.
Okay, so the worst thing for this would be then a tree or something.
Correct.
Okay.
That's exactly right.
Okay.
All right, and the final lemma is to count up the number of these sets that there can be. Now, intuitively, there could be a huge number of sets with boundary size k, where k is some large number, right? You have to count the number of these cycles that there could be of some length. But one can use a somewhat clever counting argument to show that the number of sets with boundary size k is at most 3 to the k. So it's only singly exponential in k rather than doubly exponential in k. And the way to see that, there's a simple counting argument where you start out by a node and you start to trace, well, you use the dual graph, you start to trace out these cycles. You start at any one node, you start moving around, and you have to return back to where you started. So you have to walk on this path, and each step on the path you take, you only have 3 choices, because you can't go back the way you started on a grid. And so that's where the exponential, that's why it's 3 to the power of the boundary size k. So what this shows is then that there are many large sets, so many sets which have a lot of nodes and have large values of k, but by lemma 2, the larger k is, the less likely that that set is going to be bad, according to lemma 2. So this is both of these are singly exponential in k, and if you put these together then with the union bound, these two actually cancel out. And so actually, you have to be very careful in this counting argument in order to get the final result, but what you find is in fact then that, that you get this p squared n expected Hamming error by putting those two pieces together.
I have a question about the theorem.
Yep.
So the order p square n, what is the scaling there? It's like...
Actually, you know what, I'm running out of time, so let me finish and we'll come back to this. So I'm almost done. I just wanted to give a couple of closing remarks. So the first, I wanted to point out a nice connection to percolation theory and statistical physics, which we found so we just, not surprised, you know, this happens in computer science a lot. You discover that, oh, I reproved something that's well known in some other community many years ago. In this case, these counting arguments and these probability arguments are very reminiscent of work that's done in statistical physics in the study of Ising models. And in particular, there's a whole community which works on counting the number of self-avoiding polygons in a graph. So a self-avoiding polygon is, you think of a random walk in a graph, you're walking, and then you have to somehow get back to your starting place. And the question that's asked in that physics community is, how many cycles are there of some perimeter and area? And in fact, after we made that connection, we were done proving our result, we made that connection, we were actually able to find this paper from 1999 by Jensen, he's an Australian, where he's actually computed the full table for any grid and any starting location, the precise number of cycles in that grid of some length and some area, up to symmetry. So he has those exact numbers, and it turns out that if you take those exact numbers and you refine our proof technique, you can actually get our result up to the constants. And we show that the expected Hamming error is precisely 8 times n p squared for any p less than 0.017. Now the interesting thing here is you look at this result and then you look at the lower bound and you see they're actually really close. So we've proven not just asymptotically, but we have the constants even up to only a very small loose factor that we've missed. So as I mentioned, as I alluded to a few minutes ago, one can extend this to other generative processes. That's in some sense one straightforward and immediate extension that one should do. So for example, in this analysis, I assume that the edge noise P is homogeneous, and what one could show is that that analysis only requires the property that for large cycles, the probability that that large cycle is is exponentially decreasing the cycle length. And you can imagine that there are many other generative processes that would have the same property, and that's all you need for the proof techniques. And so the takeaway points for those in machine learning are as follows. First, I want you to think about approximate inference algorithms for structured prediction in terms of recovering the ground truth. Stop writing in papers, this problem is NP hard, right? Because that's for an adversarially chosen objective, and these aren't adversarially chosen, we're learning these things. Second, there's some insights you can have in terms of how to design approximate inference algorithms. For example, you'll notice that this proof technique built up an algorithm that first looked at the clean component and then looked at the dirty components. Right? And in that way, one could design a approximate inference algorithm for linear programming relaxations where you choose the relaxation to make sure that it's at least tight on the good component. So for example, that cycle relaxation is tight if you didn't have the node observations. And so it's perhaps not surprising that when you add in the node observations, it still gets really good results. And there are many, many open problems. So one immediate one is to try to extend these results to non-binary models. It's also of quite a bit of interest to try to now develop analogous analogous models and then proof techniques to try to explain why structured prediction works well for other very different structured types of problems, like dependency parsing from natural language processing. And I'll stop there. I'm done.
Great.
I actually answered my question with the 8 ends. So that was.
Yep,
so when you did that, you had a 9p to the k over 2?
Yep.
Shouldn't that actually be 4p to the k over 2?
This one here?
Earlier. There we go. That 9p to the k over 2. I think that should actually be 4p to the k over 2.
Yeah, so this constant is in fact a little bit lower. It's the sort of, the one line proof gives 9. You do a little bit more refined analysis, you get it to be, I don't know if it's 4, but a little bit less.
Okay, and so then is the like 0.017 based on that?
Yeah, so actually no, to get the 0.017, to get this result, it shows up from as follows. So you're asking why do we have this restriction? It's very easy to see why. So this is sort of the proof sketch which puts these lemmas together. There's actually a lot of more subtle issues that I'm not going into, but this is the high level view of the sketch. So once you combine lemma 2 and lemma 4, you get these two terms. You do some expansion, you put them together, and what you get out is the following term. You get out so you get something like 81 times p to the power of L. And in order for this series, for the expected Hamming error to not diverge, you need p to be less than 1 over 81. Now 1 over 81 is actually much smaller than the number I actually gave. The way you get 0.017 is by using those results from statistical physics and by improving sort of all of the analysis. And then you can recognize that this constant is actually much smaller, and so it doesn't diverge until p is larger than 0.017.
Something to be for.
Please improve the result.
All right.
Yep.